All right, welcome back, everyone. So, this is where we left off. We have the final ordinary differential equation, and we have the boundary conditions. Good. And if you guys remember, I said that the differential equation, the ODE right here, is actually non-homogeneous. What do I mean by non-homogeneous? Okay, I'm gonna give you guys as an exercise. What is the difference between non-homogeneous and homogeneous differential equation? That's Do a little bit of research and find out. I'll link some useful resources in the description. So, and yeah, the boundary conditions are good. So the wall temperature has been specified, and at the tip, Z equals L is the tip. We have an adiabatic tip. There is no heat loss from the tip of the cooling fin. Okay, so now what we're gonna do next is we're gonna go from non-homogeneous. We're gonna go from non-homogeneous to homogeneous. Okay, no homo to homo. Sorry about that. That was a bad joke. My bad. Non-homogeneous to homogeneous. And how are we going to do that? Dimensionless variables. So I forgot what this. If anybody can really confirm what this Greek symbol is, my professor just called it squiggle. So I'm just gonna continue with the tradition and call it squiggle. All right, squiggle is just a dimensionless length. Okay, dimensionless length. And as you can see, it's my independent variable z divided by the length, the axial length of the cooling fin. And on the right side I have theta. Okay, I know that Greek letter, theta. Theta is just a dimensionless temperature. Theta is just a dimensionless temperature. And if we actually look at the structure of theta, it's the ratio of the actual independent variable minus T infinity over the wall temperature minus T infinity. And remember, T infinity is the temperature of the surrounding air. All right. So with that said, let's see. How are we gonna go from? Okay, this is good, but how are we gonna implement this into our ordinary differential equation? So first off, let's take the dimensionless length. Z is gonna equal eta times L. All right, L is constant. Keep in mind L is constant. So if I take a small change in Z is going to be equal to L is a constant times a small change in squiggle. Keep that in mind. And we can do the same thing with theta. All right. If you rearrange this, let's see if I can do the algebra correctly. Fingers crossed. Temperature as a function of Z is going to be equal to theta times TW minus T infinity plus T infinity. I think, yeah, that looks like the right algebraic form. And now a small change in temperature is going to be equal to, all right, this goes to 0. There's no change in T infinity is a constant. And this just comes out to be TW minus T infinity times d theta. So okay, so we've expressed our small changes, but now what about the derivatives? Okay, so let's start off with dt dz. Okay, dt dz. Okay, for the mathematicians out there, I apologize, this is not very formal, I know that, but I'm an engineer. We really don't care about formalities, we want to make money. All right, so dz, substitute that, you get, all right, let's switch colors, L times d squiggle. Okay, and for the temperature, you get dw minus T infinity times d theta. So this becomes, all right, if I combine these are all constants. If I combine my constants, I get t wall minus T infinity divided by the length of the fin times my new derivative term. Okay, this is a dimensionless derivative. But I actually have a second derivative, right? I'm actually dealing with the second derivative in my ordinary differential equation. So let's just do that again. Okay, boo 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 boo. keep in mind, guys, keep in mind that, let's switch a different color. Pink. Pink it is. It's not different, but it is what it is. So second derivative of temperature with respect to z. This can be rewritten as the first derivative of the first derivative. And we know this. We know this. We know this. So make that substitution. Make that substitution. You get change with respect to z is equal to this bad boy right here. So let's just copy that. Boom, boom. Oh, sorry. Oh, yeah. Got it the second time. Good. There it goes. There it goes. There it goes. There it goes. Oh, there it is. There it is. All right. So just substituted that. Very nice. Nothing fancy. Nothing fancy. I'm just doing substitutions. Nothing fancy. Okay. Oh, yeah. Don't forget to close the parentheses. So yeah, now dz. Small change in dz can also be rewritten as 1 over L times small change in the squiggle. And all of that. And all of this crap. All of this crap. Constants. Alright. And by now, if you guys remember your calculus, if you guys remember your single variable calculus, you can just pull this out. This entire term is a constant. This can be pulled out of the derivative. So what you get is, so the overall result, let's switch colors again. The second derivative of temperature with respect to z is going to be equal to the wall temperature minus the fluid temperature divided by the length squared and the second derivative of the dimensionless. The second derivative of the dimensionless temperature with respect to squiggle. All right. So let's go back to let me just go back and fetch my differential equation. We're just gonna copy this. Boom, boom, boom. All right. Be a good boy. Be a good boy. Good, good, good. And here it comes back. Here it comes back. Yep, there it is. Okay. This is the original differential equation. And for now, let's just substitute the expression for the second derivative. Let's just substitute that. And what you're gonna get is, so yeah, let's hopefully this is not getting too colorful for you guys. 2W minus wall temperature minus fluid temperature divided by length squared. The second derivative with respect to the second derivative of dimensionless temperature with respect to squiggle minus where's minus? Oh, sorry, minus. Okay, heat transfer coefficient, conductivity of the fin, and the width, half width. B was the half width. Please refer to the previous video. B was the half width. Let me just show you guys. So this was our fin, and 2B was the thickness. So B is half thickness, right? And what else did we have here? Oh yeah, dz minus T infinity equals 0. Get rid of that. We don't need it. So now you can just, now let's divide everything. Let's just isolate. We want to isolate the derivative. And I'm going to skip some algebraic steps. HL squared divided by KB times T z minus T infinity over T wall minus T infinity equals 0. And if you guys have been paying attention, you guys would find out that this is just theta. So, ladies and gentlemen, it's all making sense. We have a homogeneous differential equation. For a homogeneous differential equation, the derivatives of the dependent variable and the dependent variable can be all summed up to 0, which is what we have here. And this right here is another dimensionless number. It's called the Biot number. The Biot number. All right. So this right here is the Biot number. And Biot number, let's rewrite that. It's basically the rate of convection at surface, the ratio of convection at surface over the conductivity, over the conduction in the main body. So it's a ratio. And all the dimensionless parameters, all the dimensionless numbers are just ratios of different phenomena. Okay. So this right, of course, our final differential equation. Our final differential equation. The minus the Biot number, the in dimensionless temperature theta, all of that equals 0. And of course we need our boundary conditions. Our original boundary conditions were at z equals 0 we had t equals t wall, and at z equals L we had excuse me, we had theta, sorry, dt dz, it was an adiabatic tip, and that was set equal to 0. All right, boundary conditions. So if we make the boundary conditions dimensionless, they're going to become at eta equals 0, theta is going to equal 0. All right, I'll leave the algebra up to you guys. And at eta equals 1, okay, z equals L is going to correspond to eta equals 1. Oh, I meant squiggle, not eta, squiggle. The derivative is going to equal 0. So I'm going to end this video right here. Okay, we have the dimensionless form. We have the dimensionless form of the original model. Okay, and just to give you guys a recap, we had we started off by defining a dimensionless length, and then dimensionless temperature, and then we defined our small changes. That's the intuition I use, the small changes, and that's how, and substitution algebra made some very simple, very elementary calculus manipulations. Okay, and I was able to express the second derivative in a dimensionless form. And yep, and it was just straight algebra. We defined a new dimensionless number, the Biot number, and yeah, we had a nice homogeneous ordinary differential equation with nice boundary conditions. All right, in the next part of this video, we're actually just going to go over the solution. We're just going to talk about the solution. All of these the solutions, the general solutions are tabulated. Okay, the general solutions are tabulated and can be found in any good differential equations textbook. So the general solutions are tabulated. General solutions are tabulated. And that's what we're going to go over in the next part of this video. So thank you so much for sticking around, and I hope this was helpful.